Hello, and welcome from Zurich. I'm Mark Kasperzik, and I have the pleasure of welcoming you to our webinar on superconducting qubit characterization. Over the course of the next hour, we'll share practical tips to help you get started with qubit measurements. At Zurich Instruments, we are committed to our mission to provide the best-in-class dynamic signal instruments for advanced research and development labs. For all three pillars of our product portfolio, lock-in amplifiers, impedance analyzers, and quantum computing, we combine our know-how of digital signal processing and software development to build tools that let researchers get their results faster. In our quantum computing pillar, our goal is to help build the quantum computer by offering a system solution that covers all control needs, the QCCS Quantum Computing Control System. With this approach, we can support research endeavors starting from setups with a few qubits and provide a scaling roadmap with full backwards compatibility to 100 qubits and more. Today, we'll focus on a few qubit experiments. We will talk about signal generation and analysis functionality needed for measurements of up to 6 qubits, and how you can use a high-level programming interface to describe experiments tailored to the task, automatically translating your experiments into machine language. Today, you will see both of these aspects in action in measurements of real qubits, presented by Michele Collotto with our host, Marek Pechal, at the PSI Paul Scherrer Institute in Switzerland. Bruno Kung will cover the theoretical side of introducing the key pieces of information you need to know about the application, methods, and tools. We'll conclude the session with a live Q&A with Marek, Michele, and Bruno based on the questions you have asked during the webinar. We'll later publish answers to all your questions along with a webinar summary in our company blog. And now, without further ado, let me give the word to Bruno.
Thank you, Mark. Hello and welcome from my side. I'd like to begin this part a bit broadly with the question, why are we interested in superconducting qubits? What is great about them? And superconducting qubits actually combine a number of nice properties. They show really good coherence properties, and it's possible to control them fully electrically. No need for lasers, for instance. You can fabricate them using microfabrication technique, which is an advantage when scaling up system sizes. And it's been shown that you can combine this also in hybrid technologies, for instance, combining them with semiconductor or Rydberg atoms or NV centers. And with these many advantages, they actually have found applications in all quantum technologies. The largest one probably quantum computing, but just as well quantum simulation, quantum communication, and quantum sensing are fields where superconducting qubits are used. And the most frequently used type of qubits is the transmon qubits, and this is also the type that we'll look at in this webinar in more detail and that we use for the measurement. So let's start at looking at what is the transmon qubit. Essentially, it is almost an LC oscillator that is fabricated typically using aluminum on silicon substrate. Here on the right-hand side, you see an image of a device from Quantum Device Lab at ETH. And it's almost an LC oscillator, but not quite. So the inductor in the LC oscillator is replaced by a Josephson junction, which behaves as a very nonlinear inductor. And while a linear LC oscillator would have a quantum state ladder, which is equidistantly spaced, here already the transition from the second to third excited state, or first to second excited state, is strongly detuned from the transition from ground to excited state. So by controlling this system with a single drive tone resonant with the lower transition, you can only access these first lower two levels, and this is a qubit that you can use in quantum computing or other applications. Now going one level out, so this is a single qubit, but we also need to interface it. We need to bring signals in and out. We need to measure qubit state without perturbing its state, and we may want to couple multiple qubits. And these challenges are actually met with solutions based on coplanar waveguide engineering. Here you see a photo of a bit a larger scale of the same sample, where you can recognize control lines that actually can go right to the qubit to provide electrical and magnetic bias. And in the circuit QED architecture, which is often used with transmons, the readout is realized by passing the signal from the actual signal line through a resonator to the qubit, which can be thought of like a filter, so still isolating the qubit state. And then coupling circuits can also be realized as simple transmission lines, coplanar waveguides, as seen here, or you can place more complex circuits in between to tune the coupling as well. And in terms of connectivity here for the experiments that we look at today, we need only 3 of these lines, so a pair of input-output lines. See, these are the blue lines, the readout line, and then a single control line, which is the magenta line. One step up, the macro view. These experiments happen in a dilution refrigerator, and this is a photo from an actual setup at ETH PSI Quantum Computing Hub. And the dilution refrigerator that you see in the background provides nowadays a large sample volume down at 10 or tens of millikelvin temperatures, and the sample which resides down there is connected to with many lines. Actually, in quantum computing, it's especially a large number of lines. So you have high density wiring with including cryogenic microwave components such as amplifiers. And then at room temperature, you have a setup of instrumentation. Often it's a full rack or that scale with instruments with high requirements in terms of signal quality combined with high speed. And then these are high-end instruments that are needed for that purpose. Symbolically, in the end, all we do is send signals in and out, which is true, and we'll look at it in more detail in the following. So concretely, what do I need to measure a single qubit? And from our company, there's a clear answer in terms of what you need in terms of hardware and software. And in the hardware side, it's the SHF QC, qubit controller, which is an instrument combining all the microwave control and readout signals that you need in one box. You can get it as a 2-channel versions with 2 control channels and 1 readout channel, which is upgradable in the field, so fits small systems and provides a scaling roadmap too. And it operates from DC to 8.5 gigahertz without mixer calibration, so you can often connect the signals right from the connectors to the cryostat, that there's no need for extra amplification or other components. And on the software side, with Lab1Q, we can provide a fully Python-based measurement framework enriched with graphical tools, for instance, for pulse sequence viewing. And this software allows you to design your experiments on a high level rather than programming instruments or hardware in that sense. And it comes with a ready selection of examples that are tailored or application specific. For instance, all the measurements that we show today are contained in these example libraries. So to wrap this up, so how are these signals connected to the instrument? We have the pair of input-output lines from the what we call the quantum analyzer on the left part of the instrument, and then 1 line from the signal generator connected to the qubit charge line. So moving to the towards measurements, the first thing is we need a signal. So it's good to look at quickly how this signal comes about, how we get a measurement signal from the qubit. And in the circuit QED architecture that I mentioned, this is achieved by measuring a resonator, a signal passing through a resonator. Namely, if you measure actually a resonator transmission function, you would get maybe such a Lorentzian transmission curve in amplitude, as you see the solid line here marked with G for ground state. And because there's a coupling between the resonator and the qubit on the chip, the resonator frequency will change when the qubit state changes. And we can exploit that by measuring at a single frequency here, fMES, and looking at the amplitude and phase at this frequency will give us a contrast between ground and excited state. How to get to this point, to this configuration, we need to do 2 steps in spectroscopy. The first is the resonator spectroscopy, where we just characterize the basic properties of this readout resonator, frequency and the line width, and get things ready to have a basic qubit readout signal. And then qubit spectroscopy, we find the qubit frequency, which is the most important parameter, but then there are also anharmonicity or an upper bound for the T2, which we can obtain from the qubit spectroscopy. Looking first at the resonator spectroscopy, What is it? It is a microwave transmission measurement, and the SHF-QC, in the SHF-QC, this is done by the quantum analyzer part, which generates and analyzes the necessary signal in the digital domain, and then also up-converts and down-converts that in an analog stage using a shared local oscillator between generation and analysis. This allows us to do a phase-sensitive measurement and get the best phase stability for this measurement as well. The signal amplitude in the sample is really low actually, so it's a level of a few photons in the resonator that we aim at, and to get to these low signal levels while still having a good signal to noise, what we do is we attenuate the signal from room temperature down to the cryostat to suppress the noise at room temperature, which is thermal noise plus instrument noise, to suppress it below the thermal noise level at base temperature. And then on the way up, we have typically high Hemd amplifiers and cryogenic Hemd amplifiers, as well as sometimes a parametric amplification stage. And this latter one, the parametric amplification, would give us a readout which is quantum limited, so the only remaining noise source is the quantum noise, and all technical noise sources are suppressed. So this was the resonator spectroscopy. So then, having obtained this line shape of the resonator, we move to qubit spectroscopy, and we have to ask the question, what is the correct readout frequency? And in asking this question, we remind ourselves that this is a complex measurement signal that we look at, and so the complex amplitude A, and the quantity that we want to maximize for is the difference in complex amplitude between the signal in ground and in excited state. Starting from resonator spectroscopy alone, we cannot fully determine what is the optimum frequency, because in that picture you see here we only have the solid trace but not yet the dashed trace. So we can make a first simple guess and pick the center frequency of the resonator, which will give us sufficient amplitude contrast for the next measurements, but keeping in mind that fully optimal choice of this measurement frequency would require us to measure this contrast between the signal difference as a function of fMesh, and for this measurement in turn we need a way to excite the qubit into excited state as well, so to get both the solid and the dashed curve, if you will. Qubit spectroscopy is, for qubit spectroscopy, we add one more tone. We perform a two-tone spectroscopy measurement where we fix the frequency that we use for the qubit readout. So this is the left part of the circuit. And then we add a signal from the signal generator, of which we sweep the frequency. We can do this measurement both as pulsed or as a continuous wave measurement. In the continuous wave measurement, we just have both tones on, whereas in pulsed, we apply control, qubit drive pulse, then a readout pulse, and then we repeat this measurement many times. And both approaches have their advantages. So in continuous mode, you would get the highest duty cycle, but in turn you have to worry more about the interaction of the qubit drive and readout, and pay more attention to the powers that you apply. And on the keyword of the powers, so we have not talked about the readout powers too much, but rather about the frequencies. But powers are important parameters as well. And namely, when we look at what happens at higher drive power, for instance, this is the left side of the slide, what we would get is generally a saturation of the qubit population, which leads to a saturation of the qubit spectroscopy peak height, but also a broadening of the width. And if we go to the low power limit, where we narrow the peak and then also observe a reduction of its amplitude, we can go to the regime where we see the intrinsic line shape of the qubit and get an upper bound on T2, or lower bound maybe. Then in turn, going to higher powers, we will see additional peaks typically, for instance, GF half transition, which is a signature of a 2-photon process, bringing the qubit from ground state to the second level, excited state level, the F level, and this may be used deliberately to measure actually the anharmonicity of the qubit by measuring this peak's position. Then this was control. Then there's a readout power as well. So here the effect to be aware of is the AC Stark effect, and the AC Stark effect would cause a shift of the qubit resonance peak as a function of the number of photons that are in the readout resonator, and the average number would determine the shift that we see, and this photon number also fluctuates, which leads to a broadened peak as well, and leads to dephasing, and normally both these effects we don't want to have in the end, so we also need to measure at low readout powers to avoid these effects of measurement back action. Yeah, and with that I'd like to conclude the theoretical part and then hand over to Marek and Michele, who will guide us through these spectroscopy measurements on an actual setup.
Thanks, Bruno, and greetings from the lab. We are here at the Paul Scherrer Institute, or in short PSI, where today we'll have the opportunity to demonstrate qubit tune-up on a real sample. I'm here with Marek Pechal, researcher in the Quantum Device Lab at ETH Zurich, who's responsible for the setup of this lab. Marek, can you tell us a bit about your group and its research mission?
Hello, Michele. Absolutely. It's a pleasure to welcome you and our viewers in our lab here at PSI. So we are part of the ETH Zurich PSI Quantum Computing Hub, which is a joint center established just last year in order to develop quantum computers, specifically quantum computers based on superconducting circuits and trapped ions. Our group in particular focuses on the superconducting circuits architecture and on the potential challenges that one might encounter when trying to scale up quantum processors. And as part of PSI, we're also aiming for close collaborations with industrial partners such as Zurich Instruments, which we hope will help develop scientific instruments for use in quantum computing.
Sounds exciting, and it's great to be a part of it. So now, as we see, there's already experiments going on, and we are curious to learn more about it. Can you explain to us what's going on behind us?
Yes, so what we can see behind us is an example of a large-scale superconducting quantum computing setup. The central parts of this setup are the dilution cryostat, which houses and cools the quantum device to millikelvin temperatures, and this rack of measurement and control instruments in front of it. In fact, many of the instruments that we can see here were developed in collaborations between academia and industry. This whole setup then operates a 17-qubit device, which we use to realize an error-corrected logical qubit based on the surface code architecture. And that's a very important skill to master, because error correction is crucial if we want to operate a large-scale quantum computer in a fault-tolerant way, even in the presence of energy losses or noise. And running these fault-tolerant experiments requires extensive calibration and tune-up of the whole device. And in our demonstration today, we would like to look at some fundamental measurements for single qubit tune-up. And to this end, we have picked one of the qubits, and we have made the necessary connections to control it with a single SHF-QC instrument. For this, we just need 3 connections. So the output of the signal generator is connected to the qubit's driveline, while the input and output of the quantum analyzer are connected to the readout resonator feed line.
Thank you for your explanations. And now that we know a bit more about the setup and the lab, let's get started with the experiments. Let's dive into the measurements. The first step in qubit tune-up is the resonator spectroscopy. Here, the goal is to find the readout resonator center frequency and characterize its line shape, so we know what readout frequency to use for the subsequent qubit spectroscopy. It is a microwave transmission measurement in which we apply a continuous readout tone, sweep its frequency, and demodulate the return signal to obtain transmission amplitude and phase. So, let's carry this out and look at the data. We see here a characteristic line shape at 6.92 GHz with a width of a few megahertz. We can perform a fit and obtain the frequency of the minimum. This frequency is often a good starting point to use as readout frequency for the qubit spectroscopy, but let's note that it's not necessarily the optimal one. In qubit spectroscopy, we will now keep the readout frequency fixed and turn on the qubit drive. Here, we sweep the frequency of the qubit drive and expect to see a peak or dip in the signal when we hit the qubit resonance frequency. Knowing this frequency allows us to then conduct pulse characterization measurements, such as Rabi oscillations or lifetime measurements. In view of these subsequent steps, we have set up the qubit spectroscopy as a pulsed measurement, rather than as a continuous wave measurement. At each frequency point, we play a number of qubit drive and measurement pulses after one another. Let's look at the result. We have here already tuned the drive and readout powers low enough to clearly identify a peak in the spectroscopy signal. Its position and width tell us the bare qubit frequency and give us an indication of the qubit lifetime. Normally, we would start by finding the approximate qubit frequency at higher drive powers. With a strong qubit driving, we would also see other effects. For example, a shift of the peak position and a change of its shape, or the appearance of other peaks, notably the GF half transition. Let's look into the software mechanisms behind this measurement. I'd like to highlight 4 elements of the Lab1Q software that we use in practice. These are the device setup object, the calibration object, the qubit database, and the experiment object. The device setup object allows us to specify the structure of the hardware setup. Which devices do we use, and which signals of these devices? In this case, we have one device, the SHF-QC. We use 2 output signals for resonator and qubit drive, and 1 input signal. We can name these signals in a logical way according to where they are connected. The calibration object allows to handle the hardware settings, such as oscillator frequencies or drive amplitudes. It allows us to access and modify some of these parameters for the purpose of a specific experiment. One example shown here is we set a hardware oscillator frequency to an appropriate value we know from the qubit parameters. And that points us to the next element, the qubit parameters. We want to keep track of the qubit parameters separately from the hardware settings, and therefore we store them separately in software. We store the qubit parameters in a Python dictionary, which contains things like a T1 time or a drive pulse length for each qubit. We would maintain and update this database throughout the tune-up and always take this updated database to re-specify a new setup calibration. Finally, the experiment object represents one specific measurement, such as a qubit or resonator spectroscopy, described on a high level. To turn this experiment description into an actual measurement, the software does 2 steps. First, it compiles the high-level experiment into a hardware program, and second, it executes the program on the hardware and returns the data. Based on these data, we can do an analysis, such as a fit, and then feed back the analysis result into our quantum device database. At this point, we obtain the qubit drive frequency, and we update the corresponding parameter of the qubit database.
Now in the second part, we want to go from spectroscopy measurements to pulsed qubit control. And for these measurements, it's useful to remind ourselves of the representation of a qubit state on the Bloch sphere. Namely, I can represent any state, psi equals alpha g plus beta e, where g and e are ground and excited state, as a point on that sphere, and the north and south pole correspond to the states g and e respectively, and the longitude and latitude angles of the point correspond to the relative phase between alpha and beta, or map to the relative amplitude between these two. And how does this relate to control pulses? So if we take, for instance, a resonant drive pulse that we apply a pi half pulse, this would bring us to a point on the equator of the sphere, and the angle at which we rotate the state on the sphere is proportional to the integral under the envelope of the pulse. So if we double that by scaling the amplitude, we would get to a pi pulse that brings us to the excited state at the south pole. And the role of the phase corresponds to mapping the state on the equator of the sphere, for instance, taking this pi half pulse, but applying a 90-degree shifted pulse would get us to a 90-degree shifted position on the equator. And generally, due to the really proportionality of the final state with the phase and amplitudes of the signals, it's also apparent that these analog properties of the signal need to be really well controlled, stable, and noise-free to allow us to accurately control a qubit state. Now, how to get to this point where we have dedicated pulses to move us around the Bloch sphere? The first step to that is our Rabi oscillations. And the basic principle of these measurements is that we apply a certain control pulse and immediately afterwards read out the qubit state. So this would rotate us some angle on the Bloch sphere, and then we vary the amplitude of that pulse systematically, which would guide us through a rotation on the Bloch sphere. And the readout after this control pulse gives us a projection of the qubit state, a signal proportional to the projection of the qubit state onto the z-axis, and the implementation of this measurement is done using a pulse sequence that you see here at the bottom of the screen. So you would apply a burst of control pulses with varying amplitude, always followed by a readout pulse right after. And since we need to obtain quantum statistics to get a final sensible measurement data, we repeat this measurement many times. And some practicalities of this measurement. So first, about the drive and readout pulses. So the drive pulse, generally we want to apply a short pulse. That's advantageous as it allows us finally to apply a fast gate rotation. The disadvantage of shorter pulses is that you increase generally the leakage to higher excited states. This you suppress from the start to some degree by choosing a Gaussian envelope, which has really well-decaying spectrum at its tails. And further optimization is possible, for instance, by doing a drag pulse calibration where you tailor the spectrum to suppress, for instance, the transition to the F level and zero that out. For the readout pulse, generally also, you want to have a fast readout. As you reduce the readout pulse width, you of course get less signal, and generally you want to exploit to the best possible the measurement in this available time. A square pulse is what gives you the best integral for a given max power, and for further optimization, what you can do is pre-emphasis of the pulse to speed up the ring up and ring down times of the readout resonator. In terms of timing and averaging, it's important that the control and readout pulses are well aligned, ideally with no significant gap between them. So synchronization is important, and also taking care of the signal processing propagation delays to avoid an overlap of the pulses at the sample. You need to respect a certain relaxation time after each control readout pulse pair, and going for 3 to 4 times T1 would get you to the percentage level of residual excited state population. To speed that up further, you will need to implement active reset, which is actually rather straightforward with the SHF-QC. Then in terms of averaging, even if there's no technical noise, you still need to do quantum average over quantum statistics, and maybe 10,000 averaging here will also get you to the percent level of residual errors. Finally, then what you get are data that can look, as you see here on the right, sinusoidal oscillation of the averaged amplitude or readout signal that you have, and you can fit the sinusoid to it to obtain pi and pi half pulses. And we'll see later how this looks in practice. Beyond the Rabi oscillation measurements, you can do a suite of the 3 types that are often done together, Rabi, Ramsey, and T1. And going from a Rabi oscillation to a Ramsey, you take this calibrated pi pulse from the Rabi oscillation, and in the Ramsey you apply 2 of the pi half pulses and vary the separation, the waiting time between them, to obtain Ramsey fringes, which are a signature of the free oscillation of the qubit, and the frequency of these oscillations tells you the difference frequency between your drive and the actual qubit frequency. So this is a means of measuring the qubit frequency really precisely. And the decay of the oscillation gives you the inhomogeneous dephasing time. T1, lifetime measurements. Here you start with a pi pulse obtained from the Rabi data, and you vary the separation between a pi pulse and a readout pulse, and this gives you a decay from the excited state back to the ground state, so that T1 time, or the decay time that you measured there, is the qubit lifetime T1. And now again, back to the lab, back to Michele, who will show us the Rabi oscillation measurements in practice.
Now that we have determined the qubit readout and drive frequencies, we can move on with the Rabi oscillation experiment, which is the first step in characterizing the coherence properties of the qubit. The core element of this experiment is the application of a drive pulse to manipulate the qubit state, followed by a readout pulse to measure the state. The drive pulse rotates the qubit state on the Bloch sphere by an angle proportional to the pulse amplitude. By repeating this measurement for varying pulse amplitude, we can track this rotation on the Bloch sphere, starting out at the ground state, through the excited state, and back to the ground state. That's the Rabi oscillation. Let's start this measurement. It takes about 2 minutes, and while it is running, let's look at the software implementation. This experiment is great to illustrate the experiment definition based on the Lab1Q section concept. The Lab1Q sections allow us to define the temporal schedule of an experiment on all timing levels, starting from pulse shapes, over timing alignment of pulses on multiple signals, up to sweeping and averaging loose. For the Rabi oscillation experiment, we see here the section layout written in the Lab1Q domain-specific language. Let me go through this layout from the inside to the outside. Sections can be thought of visually as blocks spanning over multiple lines of the experimental music sheet. And each of these blocks contains pulses, spacers, or further nested sections. They're stacked from the left to the right, or in the other direction, according to the need. Here, we have 3 blocks in the innermost part: qubit excitation, qubit readout, and delay. Inside the first section, qubit excitation, we place a Gaussian pulse on the drive line by using a play instruction. In the next section, qubit readout, we similarly play a pulse, this time on the measure line. Simultaneously with the readout pulse on the signal output, we schedule an acquisition on the signal input. This is handled in a very similar fashion as a play instruction, using the instruction acquire. Instead of a pulse shape, we specify an integration weight function with which the return signal is demodulated. The first two sections, qubit excitation and qubit readout, have pulses on separate signal lines, but we want to ensure they happen after one another. The sections are stacked like in a Tetris game, and to prevent them from sliding next to one another, we can use a reserve instruction, blocking one of the lines, even if there's no pulse plate. Finally, we have a delay section, which contains a precisely specified waiting time which is needed physically to allow the qubit to relax back to the ground state. These two sections together describe the pulse pattern that we want to play. Around that pattern, we need loops for sweeping and averaging. On the first level up, we have defined a sweep of the pulse amplitude, and we make use of the sweep parameter down here in the playback instruction. A sweep like this is described in the same fashion as a frequency sweep in spectroscopy. The Lab1Q compiler will then implement the sweep in the appropriate way on the hardware, for instance as a software oscillator sweep, a hardware parameter sweep, or as a series of waveforms. And around all of this, we want to do averaging. Even if our signal was noise-free, we still need averaging over the quantum statistics for this type of experiment. So we wrap a loop around everything where we define the averaging number and also an averaging mode, whether we want to do cyclic averaging or sequential averaging. The full section layout now goes into the experiment object, which, as we've seen before, we can then pass to Lab1Q and let it compile and execute the experiment. Speaking of this, our data are ready. Let's have a look at them. We see a sinusoid oscillating between two quadrature signal levels. At the origin, we apply no drive pulse at all, and the signal is at the level of the ground state readout signal. As we increase the pulse amplitude, the qubit ends up in a superposition between ground and excited state. At the maximum, the qubit is fully in the excited state, and as we further increase the amplitude, we bring it back to the ground state. This sort of data allows us to make a first approximation to the single qubit gate pulses for a pi half and a pi rotation. We use a fit to a sinusoid to precisely identify the corresponding pulse amplitudes at 1/4 or 1/2 rotation, respectively. These pulse amplitudes can then be used in the next steps: lifetime measurements, Ramsey fringe, or single-shot readout optimization.
Now in this last part, we want to understand what advanced readout methods we can apply beyond the type that we have seen in the Rabi oscillation measurements. Namely, these are single-shot readout, multi-state readout, and also multi-qubit readout. And to dive into this, we'll have first a closer look at the signal processing inside an SHF instrument. How does this instrument get from an input signal, a microwave pulse, to an actual qubit readout signal? And it will do two signal processing parts. The first is in the analog domain, where the instrument performs a double superheterodyne frequency conversion, getting the signal from the microwave domain to the baseband, where it's digitized and exists as a complex baseband signal. And then there is a digital signal processing, where this signal is further processed by a weighted integration step and further steps. And it's this weighted integration step which is really at the heart of the signal processing. And this step is represented by the integral formula that you see here on the top. It's an integral over a time-dependent input signal v of t, a complex signal, and the integration weight Wn of t, the complex conjugate of it, where this index n denotes one of multiple integration weight units. And after this integral, we obtain a complex voltage Vn here, which is a single value, and this is further used for the subsequent steps. And if we compare the data acquired as we will acquire it in the following with what we know from Rabi oscillation measurements. So in Rabi oscillation measurements, we also had underlying a large set of these voltage values, Vn or V1, because we only used one integration weight unit. But we looked only at average of these voltages and also only at one quadrature of these averages. But we can also look at the underlying individual data points, and a useful way to plot and analyze this is using histogram or point cloud in the IQ plane, which is represented symbolically here on the right. And this image corresponds to a qubit in a single state. It gets a bit more interesting if the qubit is originating in a superposition between ground and excited, or if it's halfway in ground, halfway in excited state. And then we will expect data which more correspond to this pair of blobs that we see on the right-hand side, where we can read off this delta V GE, the difference in the readout signal between these two states, and also we can compare this with the spread or sigma of the individual blob and get so a first idea of the optimal readout direction, which maps to an integration weight phase, and obtain first idea of the signal to noise ratio. And as we enter the regime where this delta VGE is significantly larger than sigma, we can speak of single shot readout. One way to get these data and to realize in particular the top right situation, where qubit is half in ground, half in excited, is this pulse sequence on the bottom, where we apply pi pulse or zero pulse in an interleaved way and always read the qubit right afterwards, and this gives us a large ensemble of data points. One really nice thing where this becomes really visible how useful this is to look at data in this way is when there are more excited states present in the data. So for instance, if there's an excitation to the F level present in the data, that's difficult to tell from average data, but in these ensemble data, it becomes apparent as we'll have more than just the two blobs in the data, and we can identify this state. And this may be something intentional in bosonic qubits, for instance, or it may be something that we want to avoid, such as F state leakage. But if we want to go and actually basically engineer our system to use these multiple states, for instance, implementing a drag pulse calibration or implementing F-level reset to deal with the state leakage, we need a means to clearly read out and measure these individual states. And the way to do it is actually to make use of the resources on the instruments, where we have multiple integration weights and dedicate one of these weights for each of the transitions that we care about. And the question that comes there is, what is the integration weight that we need to program for measuring a given transition? The answer is actually rather straightforward. So this integration weight needs to be proportional to the complex conjugate of the difference of the raw signal traces, Vg of t and Ve of t, if it's the transition between ground and excited. And these raw traces we can obtain by a scope-like measurement using the built-in scope of the QA, and obtain a clean such trace with well suppressed noise by averaging. We can program then this experimental trace to the integration weight memory of the different units. And in that configuration here with 3 states, we could, for instance, take these 3 first units, and going from the original data from one unit that's shown on the right, we would get data where we always optimally map one transition onto the in-phase quadrature of the signal that we get, and really get the maximum information that we can have regarding this one transition. We can actually extend this on board to implement real-time state discrimination, because we can apply threshold voltages to a given value to make the decision whether this signal from an integration weight is above or below this threshold voltage, and this gives us then a signal, digital signal of a binary qubit state that we can use for qubit reader for real-time feedback, for instance. And as a last point, so this was a multi-state readout of a single qubit, but we can extend this also to multiple qubits using the same infrastructure of multiple integration weights applied to the same input signal. And just without going too much into detail, we would separate different readout signals from different qubits by separating them in frequency, both on the drive side and on the readout side. And here, for instance, start by having the first 3 integration weight units dedicated to qubit 1, and its 3 states that we use, and then the second triplet for the second frequency corresponding to a second readout resonator and a second qubit. And again, so this was the theory part, and I'm happy to hand back to Michele, who will show us these single-shot measurements in practice.
In this last measurement, we'll show how to obtain single-shot readout data and how to specify integration weights in the quantum analyzer channel of the SHF-QC. Single-shot readout data allow us to further characterize and optimize the readout, and to configure the instrument to perform real-time readout. We obtain this data using a long series of drive and readout pulses. For the drive pulse, we use either the pi pulse that we calibrated using the Rabi experiment, or we use a zero-valued pulse. This gives us 2 sets of integrated readout signal values, one with the qubit nominally in the excited state, and one with the qubit nominally in the ground state. In order to minimize the sensitivity to drifts, we interleave both acquisitions, those with pi pulse and those with zero-valued pulses. This is the section layout for this experiment. A key difference compared to the Rabi experiment is that we request the data without averaging. We can specify this using the averaging mode single shot. Specifying data handles, Q0 ground and Q0 excited, directly in the acquire instructions helps us in separating the data obtained from the instrument. A useful tool for verifying a section layout is the pulse sheet viewer. We've prepared the viewer in this tab, showing a version of our experiment with shortened delays for illustration. We see on the top half the 3 experimental signals: drive, measure, and acquire. The sections are visualized as colored blocks, and we can see the interleaved structure, for example, through the colors of the drive sections. Let's go back to the notebook and run the experiment. We then generate a scatter plot of the acquired single-shot data in the IQ plane. We see a clear separation between the data points acquired with or without applying pi pulses. This would now allow us to assign a qubit state based on the acquired quadrature values. An experiment like this provides a good illustration for how we handle pulses in Lab1Q. Pulses are crucial both for qubit control, for instance when we want to optimize a pulse shape for maximizing gate fidelity, and for qubit readout, to optimize readout fidelity. Pulses in Lab1Q are objects that we can pass to play or acquire instructions, and that we can reuse throughout a measurement. We have 2 basic ways to define pulse shapes. First, by using the built-in PICE library for standard shapes with a small set of parameters, such as pulse length or amplitude. Second, by specifying them sample by sample as a NumPy array, which allows us to apply arbitrary shapes. The nice thing is, we don't have to worry about where to place them in an AWG sequence or where on the device memory we'll have to store them. This is all taken care of by the Lab1Q compiler, and we can concentrate on the physics of the experiment.
Thank you, Michele. Thank you, Marek. You've seen now a glimpse into superconducting qubit characterization, which is really a rich collection of methods with a lot of things to explore. And what we can offer you are a set of products that make it easier and faster for you to explore these methods. You can start with the SHF-QC with a ready box with all signals synchronized and calibrated, ready to go. Also equipped with a complete feature set with the performance and scalability that you need to also go beyond single qubit experiments. And with Lab1Q, a high-level programming interface that lets you focus on experiment control rather than hardware programming. If you'd like to know more, get in touch with us. We're happy to have a conversation with you. And in particular now for the follow-up of this webinar, please stay tuned for our company blog, where we publish a follow-up blog post with answers to all the viewer questions from the webinar. We'll also share the programming code that Michele used in his part and share a collection of further reading and watching related to the topic. And now it's time for the live Q&A with Michele, with Marek, and myself.